Okay, instead of considering some simple contours on the complex normalized impedance plane, simple contours like x is equal to 0 or r is equal to 0, let's look at some contours that are more complex in that they have the form, for example here, of r equal to 2 or x equal to minus 1. Let's look at the r equal to 2 contour first. When we say r equal to 2, we're saying the contour that is formed with the locus of all points on the complex normalized impedance plane whose real part is a value of 2. What is the imaginary part? Well, it could be anything from minus infinity to 0, from 0 to plus infinity. And we plot all those points, that locus of points whose real value is equal to 2, on the complex normalized impedance plane. What we find is we form a vertical line, a vertical profile, one whose distance is exactly 2 units to the right of the imaginary axis, the vertical axis. Now, the important thing about this is that this contour is going to extend again to plus infinity and minus infinity. When that contour crosses the horizontal axis, the real axis, at that point it corresponds to an impedance, of course, whose real value is equal to 2, but whose imaginary value, because it's crossing the horizontal axis, would be equal to 0 at that point. That is the mapping, or the location, rather, of a normalized impedance, which is purely real and a value of 2. But as we move up the contour, we find the imaginary part then becomes positive, a real part of 2, an imaginary part of some positive value. As we continue to increase up that contour, that imaginary part increases, and eventually we would approach infinity. And this is important to think about. As we move up to the contour toward the end, toward infinity, we get an impedance which has a real part of 2 still, but an imaginary part that's approaching infinity. What do we call such an impedance? Well, look at the magnitude of that. A real part of 2, a reactive part, an imaginary part of infinity. The magnitude of that impedance is going to be infinite, or approaching infinity. And of course we have a name, a word for a load that has a magnitude, whose impedance, rather, we have a word for an impedance whose magnitude is equal to infinity. We call such an impedance an open circuit. Now, let's go the other way. We start at 0, where x is equal to 0 and r is equal to 2, and we move down our blue contour. As we move down, the reactance becomes negative. As we move further down, the reactance becomes more and more negative. And of course, we can eventually approach infinity as we move down the contour. We approach an impedance whose real part is 2, but whose reactance is equal to minus infinity. Once again, that impedance has a magnitude of infinity, therefore, and we would call that impedance an open circuit. Remember, there is an infinite number of impedances that would result in a magnitude of infinity, an infinite number of impedances that would be considered open circuits. 2 of those impedances are at the 2 ends of this vertical contour. Now let's look at a different contour, the x equal to minus 1 contour. Again, this is the locus of all the points, all the impedances, whose imaginary part is equal to minus 1, whose reactive part is equal to minus 1. What is the real part? Well, it could be anything that forms an infinite locus of points, where the where that contour, which is 1 unit below the horizontal axis, 1 unit below the real axis, where that contour intersects the vertical axis, the imaginary axis, is a location where the imaginary part of the impedance is minus 1, but the real part is equal to 0. It's purely imaginary, reactive impedance at that location. As we move to the right from that point, we find the resistive component is increasing. And of course, it will increase toward infinity. And as the resistance increases toward infinity, we find an impedance then, which has a real part of infinity and an imaginary part still of minus 1. Yet, if we take the magnitude of such an impedance, we would find its magnitude is infinity. So once again, that would be considered an open circuit. Likewise, if we move to the left from the imaginary axis along this red contour, we find that the resistive component, the real component, becomes negative. we move into the invalid region. As we move further and further left, the resistance becomes more and more negative until we approach negative infinity. And of course, at that point, again, we'd have a magnitude of an impedance that is infinity, and therefore an open circuit. So at the end of this red contour, on either end of the red contour, we find there is an impedance of infinite magnitude, and therefore an impedance of an open circuit. And this is important because we know where the open circuits map to on the complex gamma plane. What we're going to find at the end of all of these contours, where the magnitude and the impedances go to infinity, those points all must map to the same point on the complex gamma plane. This point over here where we have an open circuit, the value on the complex gamma plane which has a magnitude of 1 and a phase of 0. The point on the complex plane, therefore, which has a real part of 1 and an imaginary part of 0. So we'll see how that works out, but keep that in mind. It's a very important facet in terms of the mappings we're about to do, that all open circuits, and there's an infinite number of them, must map to the same point on the complex gamma plane. All right, so how do these vertical and horizontal contours, these Cartesian contours, map onto the complex gamma plane? We know a couple of mappings, as we've talked about before. The contour R is equal to 0. The vertical contour maps into a circle, the unit circle, on the complex gamma plane. And that's easily stated mathematically as all values of gamma whose magnitude are equal to 1. Likewise, the horizontal contour that says the reactance is equal to 0, that line maps onto, likewise, a similar horizontal line on the real axis on the complex gamma plane. And we can state that mathematically very simply. It's the value of all the points have an imaginary part of gamma, which is equal to 0. If you're a point on the complex plane and your imaginary part is equal to 0, then you are part of that contour. And of course, then you are on a horizontal axis that lies along the real axis. But what about these mappings we just got through talking about? R is equal to 2 and X is equal to -1. Unfortunately, they don't map into a contour that is easily described mathematically. It's not like we can say, oh, this contour has a magnitude of 0.3, or this contour maps onto a value of gamma whose imaginary part is equal to -2. Instead, what we find are parametric equations that describe these contours, that describes these mappings. So, for example, look at this equation. What do we make of this? This is a parametric statement. Again, if we look at all the points on the complex gamma plane, each point has a real part and imaginary part. If we took a point at random and we put it into this equation, we would evaluate the left side for the specific value of gamma r and the specific value of gamma I. And if we found that that left side, in fact, were equal to 0.5, then we would conclude it was a point on that contour. But if we took a different point and we evaluated it and the left side was not equal to 0.5, it was equal to 7.8 or something like that, then that point, of course, would not satisfy that equation and it would not be a point on the contour. And so it's going to be more difficult to understand the mathematical statements that result from a mapping of simple vertical and horizontal contours on the complex normalized impedance plane onto the complex gamma plane. So let's start out with a vertical contour, a contour of the form where we say, r is equal to 2, for example. What would be the mathematical statement of such a contour? All right, so we're talking about contours now, that we can describe on the normalized impedance plane by simply stating r is equal to 1, or r is equal to 6, or r is equal to 0.1, or r is equal to minus 67. R is equal to some constant value. And we're going to describe all of those contours, any of those contours, generically as a mathematical statement that says r, again, the resistive component, this is not distance from the origin, r is the resistive component of the normalized impedance, is equal to some constant we'll call CR. So, for example, if we have a contour that we describe, a vertical contour on the normalized impedance plane of r equal to 2, CR would be equal to 2. If we have r is equal to 0.5, CR would be equal to 0.5. So this is a way of parameterizing the different vertical contours that make up our Cartesian grid on the normalized impedance plane. Now, where do those vertical contours map to on the complex gamma plane? The description of those mappings are shown below. And once again, we see it is a parametric expression. We have a situation where we have an equation that depends on both the real part and the imaginary part of gamma. And again, every point on the complex gamma plane has a real and imaginary part. And if their real and imaginary part satisfies this equation, the value on the left is equal to the value on the right, then it is a point on this contour. If it doesn't satisfy this equation, it's not a point on the mapped contour. Well, how the heck do we know what this contour is going to look like? How would we be able to take this equation and make sense of what the contour is? Do we have to go through and write a program that literally inserts the values of all gammas, real and imaginary, into this equation and evaluate which ones are equal and which ones aren't, and then plot it on some complex gamma plane? Well, it turns out, of course, if you've ever studied analytical geometry, and if you have, you're of course quite lucky, you recognize this parametric expression. This parametric expression is a description on a two-dimensional plane of a very fundamental two-dimensional contour. In fact, perhaps the most fundamental two-dimensional contour. It is the equation of a circle. All right, so again, if you've ever had analytic geometry, you recognize this equation below. It is the equation of a circle. It is a parametric representation of a circle on a Cartesian plane, x and y. X being the direction in the horizontal distance, and y being the direction in the vertical distance. And we have this equation which describes a circle of radius a. Likewise, from this equation, we can discern the center of the circle. We have x minus xc. xc is a constant, some number. Y minus yc. yc is a constant, some number. Again, x and y are variables in the Cartesian plane, but xc and yc are numbers. It might be x minus 1 squared plus y minus 2 squared is equal to radius squared. In that case, what we're saying is that circle would have a center on the Cartesian plane that is located at x equal to 1 and y is equal to 2. What is the radius of that circle? Well, it depends on what the value of a is. And hopefully, again, you've seen this before. If we had a circle at the center of the Cartesian plane, we would simply have x squared plus y squared is equal to a squared, which is, again, self-evidently a equation of a circle, all the values of x and y, which are a distance a from the origin, if in fact the circle is centered at the origin. So let's see how this applies to our result for the mapping onto the complex gamma plane of our vertical contour on the complex normalized impedance plane. Our vertical contour of r is equal to CR, where there is some number. How do we apply this equation of a circle to the result shown on the previous slide? All right. So at the top here is the equation, the parametric equation that we got for the mapping of a vertical contour on the normalized impedance plane onto the complex gamma plane. And if we look closely, we see it's the same form as that of the parametric expression of a circle on a two-dimensional plane like a complex gamma plane. Of course, in this case, the variable x the Cartesian variable x is the real part of gamma, gamma r, and the Cartesian variable y is the imaginary part of gamma, gamma I. And from that, we can discern that this equation, in fact, describes a circle on the complex gamma plane, a circle whose center is located at a value of gamma r. Again, think of it as Cartesian x equal to CR over 1 plus CR. CR, again, is the value, the constant of the resistance contour. 2 or minus 4, 57, whatever that vertical contour that we first described. Gamma I is equal to 0 for the center of any and all circles. Notice it's not dependent on CR, it's just 0. And what this means is that the circle, the center of our circle, that is formed by plotting a vertical contour onto the complex gamma plane, that center will always lie somewhere along the contour described as gamma I equal to 0, the contour whose imaginary part of gamma is equal to 0. Well, we know what that contour is. That is the real axis. That is a horizontal contour lying along the real axis of the complex gamma plane. And the circle will always be centered somewhere on that line. Where on the line depends on the real part of gamma. It depends on CR. It will change as we will see, but it'll be somewhere on that horizontal contour, somewhere on the real axis of the complex gamma plane. Now, what about the radius of this circle? The radius of the circle depends on the value of CR, the resistance of our original vertical contour on the normalized impedance plane. Notice that expression for radius has the magnitude or absolute value of a result, and this makes sense because the radius of a circle must be positive. If we look at this radius, we see that as CR, the value of the resistance of that contour. If it goes to plus infinity or minus infinity, then the radius, in fact, would shrink to 0. We'd have a circle that would converge to effectively just 1 point. Conversely, if we have a value of CR, a resistance value, which is equal to minus 1, of course, this would be in the invalid region if the resistance was equal to minus 1, but if it were, the normalized resistance were equal to minus 1, we find the radius would explode to infinity. And so what we find is the circles that we make when we map onto the complex gamma plane can have any radius between 0, a point, to infinity. And the center, however, will always be somewhere along that real axis as we change the value of CR. Okay, let's do an example and see how this mapping works out for us. Let's consider the vertical contour on the normalized impedance plane, which would be R equal to 0. In other words, CR is equal to 0. We plug the value of CR equal to 0 into our radius expression, and we find that the resulting circle, when mapped onto the complex gamma plane, it would result with a circle whose radius is equal to 1. Likewise, we evaluate the expression for the center point, and we find that the location of that circle, the center of that circle, would be at a real value of 0 and an imaginary value of 0. 0, 0, the point on the complex gamma plane. Remember, the center would be a point, and so we can express it as the real and imaginary value of some gamma, or as the magnitude and phase of some gamma. In this case, gamma is simply equal to 0. Its real and imaginary part are equal to 0. It's the origin of the complex gamma plane. So when we take a vertical contour of R equal to 0 on the normalized impedance plane, and we map it to the complex gamma plane, vertical contour maps onto a circle whose radius is equal to 1 and whose center is at the origin of the complex gamma plane. Now think about this. We've seen this before, a circle who's centered at the origin and whose radius is equal to 1. We know this, of course, to be the unit circle, and this makes perfect sense for this example. So a normalized impedance whose real part is equal to 0, R is equal to 0, are impedances, normalized impedances, that are purely reactive. The resistive part is equal to 0. The impedance, therefore, is purely reactive. And so we've done this before. A impedance that is purely reactive on the normalized impedance plane, of course, all those points reside on a vertical contour aligned with the imaginary axis. When we map that onto the complex gamma plane, we know those points map onto points that are a magnitude of 1 away from the origin. In other words, they map onto the unit circle. We've done this numerous times, and this just shows that the results we had for our parametric plot for more general mappings work in this specific case. So it's a sanity check where it makes sense. One thing I do want to point out, though, is how it maps now onto the unit circle. We know our vertical contour on the normalized impedance plane will intersect the horizontal axis at the origin of the normalized impedance plane. This is the location where not only is the real part of the impedance equal to 0, but the imaginary part is equal to 0 as well. This is the short circuit case, and we know where that point on the R equals 0 axis, or contour on the complex impedance plane, we know where that origin point will map onto on the complex gamma plane. It will move to the location which we know as the short circuit location. Gamma is equal to -1. What about the remainder of this vertical contour on the complex impedance plane? Remember, as we move up, we approach positive infinity with respect to reactance, plus J infinity, that goes to infinity. And therefore that point, as we move up toward infinity, must map onto the open circuit point on the complex gamma plane. Likewise, as we move downward on the vertical contour on the normalized impedance plane to a point which is equal to -J infinity, that point, that impedance, then becomes an open circuit, one whose magnitude is approaching infinity, and that point likewise must map onto the open circuit point on the complex gamma plane, the value where gamma is equal to +1. And so what we have here, I don't know if I can do this don't have enough room in my screen here to do it like I normally do. We have a vertical contour now on the normalized impedance plane. That's again a straight line, but it morphs now onto a circle on the complex gamma plane, and the ends of that vertical impedance touch the open circuit point. And so we see what's happening, and again, it makes sense. Our math for our general contours of R equals CR predicts the contour that we know to be true for the specific case of R equal to 0. All right, let's look at a different example now and see what our parametric representation of the mapping from a vertical contour on the normalized impedance plane onto a circle onto the complex gamma plane. What would we get if that vertical profile on the impedance plane were described as R equal to infinity? All the impedances on the normalized impedance plane whose real part were infinite. The reactive component, the imaginary part, could be anything from -infinity to +infinity to 0, but the real part is infinity. Where would this circle be on the complex gamma plane? Well, according to our parametric expression, the radius of that circle would in fact be 0. What does that mean? That means we have a circle now whose radius has collapsed to 0. It has collapsed to a point. It is a circle with 0 radius. In other words, it is a single point on the complex gamma plane. Where is this point? Well, it's at the center of that circle, and that is predicted by our parametric expression as well. For this particular case, where R is equal to infinity on the normalized impedance plane, it maps to a circle of radius 0 at a point which is described as gamma having a real part of 1 and an imaginary part of 0. In other words, the point on the complex gamma plane, which denotes gamma is equal to 1 plus J0, or expressed another way, a magnitude of 1, a unit of 1 from the origin, and a phase of theta. So the rotation angle now is equal to 0. Now, when we think about this, this all makes sense. This prediction from our parametric math tells us the result, which we know to be true from our previous knowledge. All right, so let's look and see where this circle is on our complex gamma plane. Remember, again, it's a value of gamma is equal to 1 plus J0. And we see it's the green point here on the complex gamma plane. Since the magnitude of that gamma is equal to 1, it is on the unit circle. But this is a point that we've certainly seen before. It's one of our 5 standard points on the complex gamma plane. It is the point associated with an open circuit. Any impedance on the normalized impedance plane whose magnitude is equal to infinity will map to this open circuit point of gamma equal to 1. And in fact, that's all we have with respect to a contour in the normalized impedance plane that is described by r equal to infinity. Every single point on that contour has a magnitude which is equal to infinity. The vertical contour, r is equal to infinity, is an infinite distance away from the vertical axis. Every point on that contour is an infinite distance from the origin. Every point on that contour has a magnitude of impedance, which is equal to infinity, and therefore every point on that contour, r equal to infinity, must map to the same point on the complex gamma plane, that point being that of an open circuit, a point where gamma is equal to 1 plus J0. All right, so we looked at 2 extreme cases here. One where CR, our constant, was equal to 0, r is equal to 0 circle, and then we took that value of CR all the way up to infinity. R is equal to plus infinity. And we looked at the circles that occurred in both cases. For r is equal to 0, we had the unit circle. For r is equal to infinity, that circle converged to one point on the complex gamma plane, that point being the location of an open circuit. But what about values in between? Let's say we had a value of CR which is equal to 0.3, or a value of CR which is equal to 1, or a value of CR which is equal to 3. And so we'd have a contour, map a contour, let's say, of r equal to 0.3 on the normalized impedance plane, a vertical contour that was 0.3 units away or to the right of the vertical axis in the complex impedance plane. Where would that map to on the complex gamma plane? Well, we know it's going to map into a circle, and we see the circle in this case. Likewise, if I move over on the complex normalized impedance plane, have a contour r equal to 1, its real parts equal to 1, again imaginary, can go all the way up to plus infinity or down to 0 or all the way down to minus infinity. That contour will map onto a circle on the complex gamma plane, shown here. If we move over further, I think I'm running out of room here. If we move over
you make me sad.
Move over further. I'm moving over further. If you can't see it, the vertical contour from the vertical axis on the normalized impedance plane. Again, a vertical line of r equal to 3. It will map onto the complex gamma plane. All those points will transfer to the complex gamma plane onto a contour, which is shown here for the r is equal to 3 circle. So we look at this and we can see that there are a couple of things that are occurring. As the value of CR goes from 0 to infinity, the center of these circles move from the origin when CR is equal to 0. It will move rightward out toward the open circuit, which is where the center of the circle converges to when CR goes to infinity. So again, as that value of CR goes from 0 to infinity, we find the center of the circles will move from the center at CR is equal to 0 to slide along the real axis to the value of the open circuit. Notice in every case the center is on that real axis, and we saw that to be true in the general parametric form of these mappings, that the center of every circle now will be somewhere along that horizontal axis. In the case where CR is greater than or equal to 0, we find that those centers of the circles are limited to just a small segment of that contour from the origin all the way out to the open circuit point of gamma equal to 1 plus J0. What about the radius of these circles? Well, again, as CR is equal to 0, we know the radius is 1. It's the unit circle. As CR increases, becomes more positive, what we find is the size of those circles, the radius of those circles will diminish. As we slide to the right, the radius will likewise diminish. 0.3 has a larger radius than the contour for r equal to 1, and the contour of r equal to 3 has a smaller radius still. And we know as we take CR to infinity, that radius will get smaller and smaller and smaller until finally it will get 0 at the open circuit case. Now, notice every single one of these contours. R equal to 0, R equal to 0.3, R equal to 1, R equal to 3.0. All of them have a point on those circles that intersects the open circuit point on the complex gamma plane. And this is very important. We talked about this. Each of these contours on the normalized impedance plane are vertical, and they extend to plus and minus infinity. And we know then, as we move to a plus positive reactance or a minus a positive infinite reactance, or downward to a negative infinite reactance, that those impedances must map to the open circuit point on the complex gamma plane. We take our vertical contour, and again, what we're doing is morphing it into a circle where the ends of the contour have to converge to the open circuit point. And that's what is happening for every one of those circles. They all have to, when they map onto the complex gamma plane, have to morph into a circle where the ends of the contours touch the open circuit point. And so every contour in the end will always converge to the open circuit point. What we'll find for all of these contours is that there will be one point where it intersects the open circuit point. It's sort of the convergence of all the impedances, all the infinite number of impedances whose magnitudes are infinity. All those points must converge to the same location on the complex gamma plane. All right, a couple other things to look at here. Notice every single one of these circles will intersect likewise the horizontal axis, the real axis, at two places. One, of course, is at the open circuit. It is on the horizontal axis, the real axis there. But there's another point where it intersects the horizontal axis, and that would be to the left of the open circuit point. What is the physical significance of these intersections? Well, remember, the horizontal axis is the contour of all impedances whose imaginary part is equal to 0. Purely real impedances map onto the horizontal contour. And so the intersection of each of these circles, the other intersection with that horizontal axis, denotes the location of the impedance that is purely real. So, for example, if I had an impedance whose real part was 0.3 and whose imaginary part is 0, it would map to a location which is the intersection of the r is equal to 0.3 circle contour and the x equal to 0 contour, which we know to be the horizontal axis lying on the real axis of the complex gamma plane. An important specific case of this, is the r equal to 1 circle. So let's say we had an impedance whose real part was 1, normalized impedance whose real part is 1, and whose imaginary part is 0. Well, that is the matched impedance, normalized impedance. The real part's 1, the imaginary part is 0. And that matched normalized impedance, of course, plots to the origin of the complex gamma plane. And so we find a circle that a contour for all impedances whose real part is equal to 1 must intersect the origin. And when it intersects the origin, that corresponds to an impedance whose real part is 1 and whose imaginary part is 0. If we go further over, we find the green circle, r equal to 3. It intersects the horizontal axis as well, and at that point, that is the mapping for an impedance whose real part is equal to 3, normalized impedance whose real part is equal to 3, and whose imaginary part is equal to 0. Now, one final thing about these circles. Notice every one of these circles are inside of the unit circle. And this is important because the unit circle, of course, defines the valid region. Now, this makes perfect sense. We've constrained ourselves to resistances that are greater than or equal to 0. R equal to 0, R equal to 0.3, R equal to 1, R equal to 3, so forth. Since the resistance, the real part of all these examples, are positive, they must by definition lie in the valid region of the complex gamma plane. And the valid region of the complex gamma plane is in fact inside the unit circle. And so it is no surprise that all of the mappings that we have from the right side of the complex impedance plane will map into the inside of the unit circle. And this is one of the great benefits of using a complex gamma plane, is now our entire validity region fits in a finite region, a region defined by the unit circle. All right, so now let's look at the other case, the situation where this constant CR is a value which is negative. So this would be example R equal to minus 0.3, that vertical contour on the normalized impedance plane, or a vertical contour which was R equal to minus 5, a vertical contour on the normalized impedance plane. And of course, these vertical contours would reside completely in the left side of the complex impedance plane, the normalized plane. They would be in the invalid region, because these are all the impedances whose real part were, for example, equal to minus 0.3, a negative resistance, or impedance whose real part is equal to minus 5. Again, a negative resistance. So we know they're going to have to map completely into a region outside of the unit circle on the complex gamma plane, outside of the validity region of the complex gamma plane. And certainly that's the case as we see here. There's a lot of kind of complex things going on in these mappings when CR is negative. First of all, we should divide up the cases really into two parts. One where CR, that constant, is between 0 and minus 1. For example, R equal to minus 0.3. The other cases are when CR are from minus 1 to minus infinity. So an example of that would be a contour for R equal to minus 5, a circle that's mapping onto a circle for the contour R equal to minus 5. And you can see in these two cases, these two circles, they're very different. For the situation where CR is a value between 0 and minus 1, what we find is it maps onto a circle on the complex gamma plane, which is over here, sort of on the left side of the complex gamma plane, such that the circle will completely inscribe the unit circle. So it surrounds the unit circle in those cases. As the value of CR becomes more negative, from minus 0.3 to minus 0.4 to minus 0.5, what we find is the size of that circle will increase. Of course, one of the points always has to go through the open circuit point. And so as the radius increases, the center of those circles will slide to the left. They will move away from the origin along the real axis as the value of CR approaches minus 1. Now, as CR becomes minus 1, if you look at the math, we sort of have a singularity. At that point, the radius goes to infinity. The circle completely blows up. And when it does that, a circle of infinite radius is essentially a straight line. And that's kind of hard to see, but think of it of a circle that is so large that you cannot move along it and detect any curvature at all if the radius is infinity. And so that contour is shown here. It is the contour where r equal to -1. And that is it's a vertical contour on the complex impedance plane, and it actually maps into a vertical contour on the complex gamma plane, shown here. And again, really what that is a circle with an infinite radius. Now, let's say we punch beyond the sorry, my printer is let's say we punch beyond the value of CR equal to -1. Hold on a second.
You're wasting our time, Earth creature.
I'm sorry. So let's say we have a value of CR is more negative than -1. In this case, we have circles that are completely to the right of the r equal to -1, or to the right of the r is equal to -1 contour. They're on the right side of the of that contour. For an example here, r equal to -5. And so clearly none of those points reside inside the unit circle, but all of the points reside outside, but they don't inscribe the unit circle. They're simply on the right side of the complex gamma plane over here. As the value of CR becomes more and more negative, what we find are two things. One is the radius of those circles becomes smaller and smaller. So the example here we have is r equal to -5. If I go to r is equal to 10, it would actually become a smaller circle. And in fact, as CR approaches -infinity, we know what must happen. If we have an impedance whose real part is equal to -infinity, that's an impedance whose magnitude is equal to infinity, and therefore all those points must, in fact, map to the open circuit point on the complex gamma plane. Once again, we see a circle that is, as the radius gets smaller, it converges to the open circuit point on the complex gamma plane, just like it did on the other side as CR approached +infinity. We had a circle that converged to open circuit. Now, if we have a contour where CR is equal to -infinity, again, that circle converges to the open circuit point on the complex gamma plane. So it's sort of an interesting and kind of a complex mathematical manifestation of the solutions that we had. And again, really, it divides itself into two pieces. One where CR is between 0 and -1, and then another one from -1 to -infinity. Are these contours going to be very useful to us? Well, not really. Certainly, all these values are for impedances with negative resistances, and so they're all in the invalid region. And as long as we stick to passive devices, they are really are not of much concern to us. All right, so just putting everything together, putting everything on one complex gamma plane, now we see all of the contours that have the form r is equal to some constant CR. And CR could be anything, in this case, from -infinity to 0 to +infinity. And we see all the circles that result in those cases. Once again, the circles, the contours that we're really interested in are the ones in the validity region, and therefore the ones inside of that unit circle. All right, so now let's move on to the other Cartesian contour that we considered on the normalized impedance plane. And those contours are the form x equal to some constant. All the impedances whose imaginary part is equal to some specific value. For example, x is equal to -2 would be a horizontal contour 2 units below the horizontal axis, the real axis. And that would, again, correspond to all impedances whose imaginary part is equal to -2. Impedances that might have a real part of +infinity, or a real part of 0, or a real part of -infinity, or anything in between. The important thing is, in every case on that contour, the imaginary part is equal to -2. Or we might have one where x is equal to 0.5, a contour that would be half a unit above the real axis on the complex impedance plane. So again, the horizontal Cartesian contours on the complex impedance plane, and we want to see how each of those horizontal contours maps onto the complex gamma plane. I'll just present the results from that mapping. Again, this is what Smith did in the Smith chart, was to go through and do this, what we call conformal mapping, of taking the mapping from the Cartesian grids, horizontal lines, and vertical contours on the complex impedance plane, and mapping them onto the complex gamma plane, or more specifically to the validity region of the complex gamma plane. So he did the mathematics, and this is the second of the results, the parametric description of the locus of all points that are mapped from a horizontal contour on the normalized impedance plane onto the complex gamma plane. Now, if we look at it, it is also the equation of a circle. It has exactly the same form, but this is a very much different circle than what we had for the vertical contours, where we had impedances for specific values of resistance. So let's look at these circles and what they tell us. All right, so let's look at this equation. This parametric description of the circles on that are mapped onto the complex gamma plane. And we see, again, it is a description of a circle. And from the math, we can ascertain both the center location of the circle and the radius of the circle. First, the center. Well, the real part of the center, I should say, the center of the circle is a point on the complex gamma plane. And the real part of that location of that gamma must be equal to 1. Notice this is independent of Ci. And because of that, it means that the center of all the circles that are mapped in this way must be along a contour that is described as gamma r equal to 1, a vertical contour on the complex gamma plane. The imaginary part of the center of the circle is dependent on Ci. And so what we'll find is the center will kind of slide up and down this vertical contour of gamma r equal to 1 as we change the value of Ci. If we look at the radius, look at the right side of the equation, 1 over Ci squared, that becomes the radius squared, and therefore the radius is going to be equal to 1 over the absolute value of Ci. Again, it's the absolute value because the radius must have a positive value, whereas Ci could be positive or negative. We see here that the radius could go to infinity, an infinite size circle, when Ci goes to 0. Conversely, as the magnitude of Ci goes toward infinity, we find that the radius, in fact, will collapse to 0, and our circle will become a single point. Where will that point be if Ci goes to infinity? Well, when we look at it, the center here, we see that that point will be at a value of gamma r equal to 1 and a value of gamma I equal to 0. Think about where that is on the complex gamma plane. All right, so let's go ahead and plot the mapping of several horizontal contours on the normalized complex impedance plane onto the complex gamma plane. And of course that mapping results in circles, and we've seen these circles here for different values of Ci. If we look at this, the values extend in our example from let's see, what's my largest value of x equal to 3 to a most negative value of x equal to minus 3. There's a lot of stuff going on in this plot, so look at it carefully. First, identify where the origin of the complex gamma plane is. Also, identify where the unit circle is. And so the validity region of this plot is again limited to the unit circle here on the left side of the plot. Now, there's a lot of stuff that's going on outside of the validity region, of course. One of the things that you should notice here is that every one of these circles intersect the open circuit point. And again, we've talked about this, it has to be the case. We have horizontal contours, and if we head off to infinity on either end, what we find is the resistive value will approach positive infinity, or the resistive value will approach negative infinity. In either case, the magnitude of the resulting impedance will be infinity, and therefore the endpoints of those horizontal contours must map onto the open circuit point on the complex gamma plane. And in fact, every single one of these circles do. And as they approach that open circuit point, it's because the resistive component, remember the reactive component, the imaginary part is fixed, x equal to 3, x equal to minus 2, or whatever, but the resistive component changes from minus infinity to plus infinity, and as it approaches either minus infinity or plus infinity, it approaches the open circuit. Now, one of the interesting things about this is you can kind of tell how it approaches that open circuit point. As r goes to plus infinity, of course, it will approach the open circuit point, but it must be inside of the valid region. And so as the circles loop around here, as they approach the open circuit point from inside the unit circle, that's resistance going toward infinity. Then they loop outside of the validity region, and they come back and they approach the open circuit from the opposite side. And of course, in this case, they're outside the valid region. This is a case where the resistive part of, let's say, x equal to 3 is approaching minus infinity as it converges to the open circuit. All right, so let's go through and divide up this plot into two sections to try to make some sense of it. First of all, let's consider the cases where the value of Ci is positive. In other words, the reactance is inductive. The imaginary part is positive there. And what we find here are a series of circles that lie in the upper half of the complex gamma plane. The imaginary values of gamma, in this case, are all positive. So it's interesting, when the reactive component is positive, then the imaginary part of the impedance is positive, then likewise the imaginary part of gamma must be positive as well. And so the upper half of the complex gamma plane is known as the inductive region. All the circles that exist there correspond to reactances that are positive, in other words, inductive. What happens as the value of Ci increases from 0? What we find are a couple of things. One is that the radius of these circles will diminish. Remember, as Ci goes to infinity, the radius must, in fact, diminish to 0 as it approaches the open circuit point. And therefore, conversely, as Ci becomes smaller, approaches 0, then the radius, in fact, will start to expand. The other thing that happens then as Ci, the value of Ci becomes greater and greater, more and more positive, is that the center of the circle will move. It will slide down a contour, which is the contour of gamma r equal to 1. Remember, we found the center of every circle must be on this contour. The value of gamma r is equal to 1 for every circle center. The imaginary part will change. In this case, it'll all be positive. But as the value of Ci becomes smaller, then the center point of the circles will move up that gamma r equal to 1 contour. And likewise, as Ci becomes larger, it will slide down toward the open circuit point. Another thing to point out that's very important here is that these circles where the reactance is constant, has some value of 2, for example, those circles neither lie completely in the valid region or outside the valid region. Part of every circle is within the valid region, and part of every circle is outside the valid region. Why is this? Well, it's pretty simple when you think about it. Remember, the complex impedance plane, the normalized complex impedance plane, these are horizontal contours. Half of those contours are in the valid region of the complex impedance plane. They have resistive values which are positive. The other half of that horizontal contour is in the invalid region. It has resistances that are negative. And so when we do the mapping, part of the mapping must be within the valid region and part must be outside of the valid region. And that's what we find here for every case. Now, notice the circles intersect the unit circle here in two places. The first place it intersects the unit circle, of course, is at the open circuit point. We always must converge to the open circuit point. Excuse me. The second point where these map circles intersect the unit circle, now we can look at and see that it changes as a function of CI. What do those points represent? Well, remember, the unit circle corresponds to all impedances whose real part are equal to 0. So we could describe that circle as the R is equal to 0 circle. We could describe, let's say, the gold circle here as the x equal to 0.5 circle. And so the intersection of the x equal to 0.5 circle with the R equal to 0 circle is an impedance of 0 plus j.5. That is the mapping of the impedance j.5 to the complex gamma plane at the intersection of those two contours. As the real part of that impedance increases from 0, what we find is then that contour, that mapping, will move into the validity region. The resistance is becoming positive. That's part of the validity region. We move into the validity region. As the real part of the impedance, the imaginary part again is 0.5, but the real part becomes more and more and more positive. What we find is we move along a contour of our mapping and we approach the open circuit, as we must, as the real part of that impedance goes toward infinity. The imaginary part's 0.5, the real is approaching infinity, because that magnitude of that impedance will be infinite also. It must map toward the open circuit. So again, the circle then will approach the open circuit point. And so there is some region of every circle that lies within the validity region. And it begins at a point where the circle intersects the unit circle. That's where the resistive part of the impedance is 0. And then it will proceed toward the open circuit point on the complex gamma plane. And that's the point where the resistive part of the impedance goes toward infinity. If we go the other way, if we have a situation where the resistive part starts at 0 and then becomes more negative, now we slide outside of the unit circle. And most of the circles then, the mapping of the form x equal to some CR, most of those circles then, most of the distance, I should say, lies outside of the validity region, outside of the unit circle. There's sort of just a small portion of those circles that will reside inside that validity region. All right, so now let's look at the other case, the case where the constant CI is a negative value. And that would correspond to a reactance, which then is capacitive. And in this case, we find all of the circles, all the mappings of the impedances. In this case, contours, horizontal lines that are below the horizontal axis on the complex impedance plane. Those contours map onto circles that are likewise below the horizontal axis on the complex gamma plane. And so the lower part of the complex gamma plane is known as the capacitive region. Impedances that have a negative reactance will always map to a point which is below the horizontal axis in the complex gamma plane. So we call this the capacitive region. Otherwise, the circles that result are just sort of a mirror image of what we had for the positive case. Once again, as the value of CI approaches a minus infinity, the radius of each circle will become smaller and smaller until it converges excuse me, to the open circuit point. As the value of CI becomes more and more negative, the center of the circles likewise will slide toward the open circuit point, but they'll slide again along this contour gamma R equal to 1. As CR becomes more negative, it slides upward along that contour to the open circuit point. So there's kind of an interesting thing here when you think about it. We go back to the vertical contours of the form R equals to CR. those vertical contours all had circles mapped onto circles whose center was along the contour gamma r equal to 0, the horizontal axis of the complex gamma plane. For the other circles where we're mapping horizontal contours on the complex impedance plane onto circles on the complex gamma plane. For this case, we find the centers are always along a contour, which is described as gamma r equal to 1. The centers slide up and down it. Well, look at where the intersection of the gamma r equal to 1 contour is and the gamma I equal to 0 contour is, where the horizontal axis. Those two contours intersect at the open circuit point. So the open circuit, with respect to plotting impedance onto the complex gamma plane, is a very interesting point in that there's an intersection of many things happening at that location. And again, it really comes from this mathematical problem where an impedance whose magnitude is infinity, an impedance whose distance is infinite away from the origin on the complex impedance plane, there's an infinite number of those impedances. There's a circle with a radius essentially of infinity on the complex impedance plane. Every single one of those points must map to this single point, the open circuit point, on the complex gamma plane. Okay, so we showed the cases where CI were positive. We had circles in the upper half of the complex gamma plane. We looked at the case where the contour where CI was negative. They map onto circles that are in the lower case of the lower half, rather, of the complex gamma plane. Let's look at the specific case where CI is equal to 0. In other words, an impedance whose imaginary part is equal to 0. Of course, this is a purely resistive impedance, a purely resistance, real valued impedance. If we look at our circles or contour math, it says that the radius of the resulting circle must be or goes to infinity. And what we find is, once again, kind of like we had before, effectively we have a situation where we have a very, very big circle, one whose radius expands to the point that it effectively loses its curvature. As we move along the circle, we cannot detect any curvature, and this movement would happen along the real axis, along the contour, then, which is mapped for x equal to 0. Yet, once again, this doesn't surprise us. We know what the mapping for x equal to 0 is. If we have a purely resistive impedance, we know that it maps to the complex gamma plane along that horizontal axis, along the real axis of the complex gamma plane. We've seen this, we've talked about it several times, and once again we see that the math that is constructed for the Smith chart likewise verifies this situation. All right, so we looked at specifically when CI is equal to 0. Now let's look at CI is equal to plus or minus infinity. So we're looking at horizontal contours on the normalized impedance plane that are either an infinite distance above the horizontal axis or a infinite distance below the horizontal axis. And if we look at the math, we find the radius of the resulting circle must be 0, and the center, and we talked about this earlier, has a value which is located at a real part of 1 and an imaginary part of 0. In other words, 1 plus j 0, or 1 times e to the j 0. In other words, a gamma of 1, the point which is the open circuit. And of course, this makes perfect sense. So why does it make perfect sense? Well, if contour has a value of x equal to infinity, then the magnitude of that impedance is going to be infinity regardless of the value of r. It will all converge to the open circuit point. Likewise, when x is equal to minus infinity, any impedance whose reactive component is negative but infinity, the magnitude is equal to infinity likewise, and it must likewise then plot our map to the open circuit point on that complex gamma plane. So again, this makes sense both mathematically and both physically about what we understand of the complex impedance plane and the complex gamma plane. All right, so let's go back to the first plot we had. where we show all the circles, both for CR positive and negative, and CR is equal to 0, X equal to 0, for example. And again, one of the important things to think about or to understand is that these contours, each one of them, reside partially in the valid region and perhaps mostly in the invalid region. Every circle intersects the open circuit as it must, and every circle intersects the unit circle at another point. And this is where again, the resistance of the impedance would be equal to 0, since the unit circle is the R equal to 0 contour there. What we're going to be interested in microwave engineering primarily is the valid region. There are some situations for amplifier designs when we have active devices where we will be interested in these contours outside of the valid region. But if we concern ourselves just to passive devices, what we'll find is the valid region, where the resistances are positive, are what we're interested in. So what we're going to do is take our scissors and essentially cut around the valid region and extract the portions of these contours which in fact reside inside of that valid region. All right. So, putting this together, if we have contours of the form R is equal to some CR, as long as CR is positive, what we find is they map into circles which lie completely inside of the unit circle. They are completely in the valid region. For contours of the form X equal to Ci, those horizontal contours in the complex impedance plane, they map onto circles which partially reside in the validity region, but mostly outside the validity region. And so therefore, if we take both of those contours, both for the vertical contours R equal to CR and the horizontal contours X equal to Ci on the complex impedance plane, and we map them into circles, and then just cut around the unit circle and consider only the portions of those mappings inside the validity region, what we have is a very important tool to microwave engineering, an iconic tool in electrical engineering, and that is called the Smith chart. All right, so here is a image of a Smith chart, and the most important fact about the Smith chart, one that again is not appreciated by by a significant amount of electrical engineers, is the fact that the Smith chart is printed on the complex gamma plane. All right, don't let it doesn't say it's on the complex gamma plane, but don't let that fact ever leave your mind when you look at a Smith chart. The Smith chart is circular, and the boundary of the Smith chart is the unit circle. We are plotting the mappings of the complex impedance plane onto the complex gamma plane that reside inside of the validity region, that correspond to impedances whose real part are positive resistances there. There is an origin of the complex gamma plane, and it's right there in the center of that circle. We have an imaginary axis of gamma, we have a real axis of gamma. It's the exact same gamma plane that we had before. The locations of the short circuit are the locations as it was before, the location of the open circuit as it was before. It is the complex gamma plane. The only difference between the complex gamma plane and a Smith chart is that we have plotted the mappings from the rectilinear grid, the Cartesian grid of the normalized complex impedance plane. We've mapped them onto the validity region in the complex gamma plane, and we've made those mappings explicit. And that's why you see a series of circles, all right, that expand outward to a radius of 1, and those of course correspond to the mappings of the R equal to CR, the vertical contours of the grid, of the Cartesian grid in the complex impedance plane. We also see a series of partial circles there, and those again are the parts of the mapping from the horizontal Cartesian grid, the X equal to Ci portion of the complex impedance plane mapped onto the gamma plane, and again excluded the regions outside of the unit circle. That's what the Smith chart is. And again, it's on the complex gamma plane, so all of the transformations that we did on the complex gamma plane, all those parametric plots of reflection coefficient as we move from one point to the other, striking a circular arc over some angle which is 2 beta L, all those things that we did before we put these contours onto the complex gamma plane are still valid, and we can still do them. What we're going to find is that allow us to solve problems where we go from impedance to reflection coefficient and reflection coefficient back to impedance. We can do them almost instantaneously with this graphical tool that we call the Smith chart. So again, if we go back to the normalized impedance plane, real and imaginary, what we're going to go through is take these horizontal contours, which are associated with impedances of constant reactance, x equal to 1, x equal to 0, x equal to -1. And likewise, consider the vertical contours where the resistance values are constant, r is equal to 0 or r is equal to 1. Notice the intersection of these points have some of our standard values that we've considered. We have a case where r and x are equal to 0. That would be a short circuit at the origin of the normalized impedance plane. We have a case where the resistance is equal to 1 and the reactance is equal to 0. And of course, this would be the matched impedance on our normalized plane. We have a case where the resistance is equal to 0 and the reactance is equal to +1, and this would be the inductive match reactance point. And likewise, one where the reactance is equal to -1 and the resistance is equal to 0, and this would be the capacitive match reactance. So these are the usual points on our complex impedance plane. Let's see what happens if we try to map the whole structure now onto the complex gamma plane. We know how to do that. We have vertical contours, horizontal contours, points that we've mapped. Let's just try to put the whole thing and map it onto the complex gamma plane. So if we do the mapping onto the complex gamma plane, this is what it looks like. This is what we get. Again, the same artifacts. I tried to color code them. We have a matched impedance. We have a short circuit. We have an open circuit, which is at the extrema of all of the contours that we have. We have matched reactances at top and bottom of the complex gamma plane. And so we can see where we took that whole structure and we moved it, mapped it onto the complex gamma plane. And again, this is essentially a Smith chart. Only in the Smith chart we do more than just a few horizontal contours and more than just a few vertical contours. The result that we get from this mapping is what we call a curvilinear grid. For the Cartesian grid that we started with of vertical contours and horizontal contours, we call that a rectilinear grid. We have the vertical contours and the horizontal contours clearly when they intersect such that they are perpendicular, 90 degrees with respect to each other. When we map this onto the complex gamma plane, what we, of course, lose is the rectilinear grid, the Cartesian grid. The contours are clearly no longer vertical lines and horizontal lines, but they are still a curvilinear grid in that at any point when we look at the contour of one x equal contour to one r equal contour, our circle, what we find as we converge to that point, we see that they cross at an angle that is always 90 degrees with respect to each other. And so what we have is a curvilinear grid on the Smith chart. We transform or map the Cartesian grid of the complex impedance plane onto a curvilinear grid on the complex gamma plane, and that is the Smith chart. So to try to graphically show this mapping, and again, you think about it, this is kind of profound from the standpoint that we're taking the validity region on the normalized impedance plane, which is a half-infinite space. It's the right side of the complex impedance plane. And we're taking that half-infinite space and we're mapping all of those points into a finite size, a unit circle. And so what we're doing is taking, again, a very large space and crushing it into a smaller space. And if we could watch this transformation happen, it might kind of look like something here on the right side. I had a grad student a number of years ago who had a job interview with a very well-known microwave company, and they had technical interviews. And one of the questions was, explain to me how the contours of the complex impedance plane map onto a Smith chart. Now, how do you answer that? It's taken me, this whole presentation to try to describe that. How would you answer that in a job interview? And he said he was, kind of perplexed about how to answer that. It was such a difficult and complex or long, involved process of doing it. And he said, so it was lost for words. He simply held out his hands like this. Well, you need a bigger screen. He went like this, and then he went like this, and then he just kind of turned his hands into a circle like this. And they said, that's right. And he got the job. So that's really kind of what's going on. Think about this in your mind, the transformation of the rectilinear grid, the Cartesian grid, as we crush it into the unit circle. So we crush it inside the unit circle, and again, that's what the Smith chart is. The important thing to remember about the Smith chart, though, is it's on the complex plane. And everything we learned about the complex gamma plane, everything we learned about the complex gamma plane still applies for the Smith chart. All we've done is put some underlying mappings from the Cartesian grid of the impedance plane onto the complex gamma plane. And again, this allows us to convert from impedance to gamma and gamma to impedance instantaneously in a graphical means. And we'll show how that will be helpful to us to solving problems associated with a terminated transmission line.